Welcome to Lecture 18, Dry Friction. In this lecture, we'll look at the characteristics of dry friction and then look at the typical groups of problems involving dry friction. Up until this point in the course, we have simplified some of the problems we've been working by ignoring friction. An example of this is where we have a rigid body in contact with a surface, whether it be a wall or the ground, and we've assumed that the surface is perfectly smooth, allowing us to show a reaction force that is perpendicular to the surface and not showing any friction force along the surface. This simplified that type of problem in that we would only have one unknown at that reaction point versus two unknowns. Another example of this is when we've had cables or ropes going over pulleys. We've assumed that those pulleys are frictionless and are not offering any resistance of their own to the movement of the rope or cable going over it. In reality, however, no perfectly frictionless surface exists. When two surfaces are in contact and one attempts to move with respect to the other, tangential forces, which we call friction forces, will always develop. Let's consider a block of weight W that's placed on a horizontal plane surface, the ground, as shown in the figure on the left. And let's draw a free body diagram of that block as shown on the right. And we show the weight acting down through the center of gravity of the block. And the reaction force provided by the ground, the horizontal surface, is going to be perpendicular to the horizontal surface as well as the bottom surface of the block and act vertically upward, and we'll call that the normal force since it's normal or perpendicular to the horizontal surface and the bottom of the block. Now we need to realize here that that normal force that we're showing as a concentrated force in actuality is a distributed force across the bottom of the block. So I'll draw that in. And it's a distributed force. And we know a little more about these. We've been talking about distributed loads or distributed forces, same thing. And when the for this situation where the block is just resting on the ground with no other forces applied to it, the intensity of that distributed force acting upward on the block is constant. And from what we know about distributed loads, we can replace a distributed load or a distributed force by a concentrated force where the magnitude of that concentrated force is equal to the area of the distributed load, in this case rectangular, and that concentrated force acts through the centroid of the area. So this should be nothing new here, but we need to point this out as we develop our story on friction. Now let's apply a horizontal force P to the block, but before we do that, we'll acknowledge that the horizontal surface that the block is sitting on is not perfectly smooth, it's not frictionless, and the bottom of the block, that surface is not perfectly smooth or frictionless. And when the block attempts to move with respect to the horizontal surface, that frictional forces are going to develop. And let's assume that the force P we're applying is small enough so that the block will not move for the time being. And let's consider a free body diagram of that situation. So we'll show the weight of the block acting through the CG. We'll show the force P. We'll show the normal force. And now that the block is attempting to move but is not moving because of friction, there's this frictional force opposing the attempted motion. Now notice what happened to the normal force. I'm not showing that acting up through the center of gravity of the block right underneath the weight. And that's because, remember, that normal force that we're showing as a concentrated force is actually a distributed force. But now that distribution looks more like this, where the intensity gets larger as we move across the bottom of the block from left to right. Okay, the intensity becomes larger the closer we get to the right edge of the block. And from what we know about distributed loads, distributed forces, that we can show a single concentrated force that has a magnitude that's equal to the area of this distribution that acts through the CG, I'm sorry, not the CG, the centroid of that distribution. So we're showing that normal force now acting through some centroid, the centroid location of that distributed load. Now, hopefully this is intuitive, that when we start pushing on the block and it's not moving, that the block is going to, it's not, we're not saying it's going to tip, but you can, hopefully it's intuitive that distributed normal force is going to take a shape something like I've shown here, that it's going to be of higher intensity on the right side of the block surface and lower intensity on the left side of the block surface. And if you look at this from an equilibrium perspective, and some moments about any point on the block, remember the block's still in equilibrium, it's not moving, that if that normal force, that concentrated normal force, has not moved from out underneath the weight force, then there's no moment to offset the moment caused by P and F. And so hopefully you can see that when you look at this. As the magnitude of the horizontal force P is increased, the magnitude of the opposing frictional force F also increases until what's known as the limiting static frictional force is reached. And we denote the limiting static frictional force by F sub S. And at this point, the block is just about to break away and start moving. And we call that condition impending motion. Now the limiting static frictional force, which we called F sub s, is directly proportional to the normal force by the constant of proportionality mu sub s, and mu sub s is known as the coefficient of static friction. The coefficient of static friction is strongly dependent on the nature of the surfaces in contact. It's independent of the area of the surfaces in contact, and it's determined experimentally for different contacting surfaces. The limiting static frictional force, F sub s, combines with the normal force, N, to create what's known as the resultant force, R sub s. And the angle that R sub s makes with N is called the angle of static friction, and we refer to it as phi sub s. Now the angle of static friction is related to the coefficient of static friction by this equation, where the angle of static friction is equal to the inverse tan of the coefficient of static friction. Once the block starts moving, the frictional force actually drops. This may not be intuitive, but think about a time where you've tried to push something across the floor, and you probably experienced that it takes more force to get it to move than it does to keep it moving. So that's what we're talking about here, and it's expressed in this graph here, where we're pushing on the block with a force with P. We start out with the magnitude of P being 0, and as we increase P, the force P, the horizontal force P, the frictional force increases not just proportionally, but it's actually equal and opposite to P to oppose the motion, until that frictional force reaches F sub s, at which point any more increase in the magnitude of P causes the block to break away, and once it starts sliding, the frictional force actually drops, and we call the frictional force when the block is sliding or when the object is in motion the kinetic frictional force, and denote it by F sub k. And like the static frictional force, F sub k is proportional to the normal force by the constant of proportionality mu sub k, where mu sub k is known as the coefficient of kinetic friction. Similar to the angle of static friction, we have the angle of kinetic friction, which we call phi sub k, and phi sub k is the angle between the normal force and the resultant force of F sub k and the normal force, and phi sub k is equal to the inverse tan of the coefficient of kinetic friction. Most problems involving dry friction will fall into one of three groups. The first group we'll look at is the no apparent impending motion. And in this type of problem, you'll be asked to determine whether the body will remain at rest or will motion occur. And you'll be given the coefficient of static friction. And in this case, let's look at this example here. There's actually two different contact points that have different coefficients of static friction. So you may be given multiple coefficients of static friction. You'll need to draw any necessary free body diagrams and then use those free body diagrams to determine what frictional forces are necessary for equilibrium. In other words, what frictional force is necessary to for the body or possibly multiple bodies to stay at rest. You'll calculate those frictional forces necessary for equilibrium, and then you'll compare them to their respective limiting static frictional forces, which you can calculate by the coefficient of static friction times the normal force. So remember that mu sub A times N sub A is just the F sub A S, if you will, the limiting static frictional force for that situation. And again, for our example here, that would be the situation here. And then for point C, you would compare the force necessary for equilibrium to the limiting static frictional force at C, which you can calculate by mu sub C times N sub C. And if the force necessary for equilibrium is less than the limiting static frictional force, then you're good to go. Motion is not going to occur. It will stay at rest. It's when this force, it's when the frictional force needed for equilibrium exceeds the limiting static frictional force that motion will occur. The second group of problems involving dry friction is impending motion at all points of contact. So in the example shown here, we're asked, for what value of theta does the body begin to slide? So when we look at this problem, I think it's obvious that the greater theta is, the larger theta is, the less likely the bar is to slide. And as theta gets smaller, it's going to approach a value where motion is impending. There's an impending motion. So in this problem, we're given mu sub S. Actually, there's two mu sub S's, two different contact points. We draw a free body diagram of the bar, and then we assume impending motion. We set the frictional force at A on the free body diagram equal to the limiting static frictional force for A. Remember, this is just equal to F AS. And we set the frictional force at B equal to the coefficient of friction at B times the normal force at B, which is just our limiting static frictional force at B. So we forced it to be in equilibrium, but with the state of impending motion. And then we use the equations of equilibrium available to us to solve for theta. And in this case, that's the value of theta, the value of theta that you solve for. If theta gets any smaller than that, then the bar is going to slide. The third group of problems involving dry friction is impending motion at some points of contact. Here's an example of this type of problem. And you're asked to determine for what value of P does the body begin to slide. And unlike the example on the previous slide, where there was a single rigid body that had 2 points of contact, each with their own coefficients of friction, this is 2 rigid bodies connected by a pin at B, and each rigid body has a point of contact with a specific coefficient of friction. So to solve this problem, you'll have to consider 2 different cases. The first case will be that slipping will occur at A first. In other words, you'll assume that slipping will occur at A first. And to do that, you'll set the frictional force at A equal to mu sub A times the normal force at A. Remember, this is just the limiting static frictional force. So you're assuming that impending motion will be caused by, will occur at point A before it will occur at point C. Remember that mu sub A, n sub A is just the limiting static frictional force. With that assumption and with setting F sub A to mu sub A, n sub A, you solve for P. Set that aside for a moment. Then solve the second case where you assume slipping is going to occur at C first. Force F sub C to be equal to the limiting static frictional force. Solve for P for this case, and then compare the values of P that you calculated for both cases, and the case with the smaller value for P will actually be the one that actually occurs. In other words, if the value for P was smaller for case 1 than it is for case 2, then when P reaches that smaller value, slipping is going to occur at A. It doesn't have, and C will not have slipped because you hadn't reached the value of P necessary for that slippage to occur.